and together with my colleague Felix Gotzler, I'm working at the chair of automotive technology at Technical University of Munich. Our goal is to analyze different mobility systems. Mobility systems consist out of the infrastructure, the vehicles, and the operating strategy. And SUMO is the tool we use to modify different parameters of these systems to find the best possible solution given certain circumstances. And today we will talk about the system called personal rapid transit. So now our slides are moving. So we are facing an increasing urbanization that leads to an increasing traffic demand. And just to state a few examples, when we would like to use very public transport systems, it's most of the time inconvenient, especially in the rush hours in the morning, and it's quite expensive. If I focus now on the aspect of convenience, I could just take my own private car. However, I tend to end up in traffic jams. And these are just a few examples. With active mobility, it's a similar problem regarding the capacity, so it can't offer that capacity with active mobility. And as you can already see, we have a potential solution in mind called personal rapid transit, or short PRT. A personal rapid transit system is consisting out of small autonomous vehicles. Depending on the design, it offers space for 2 up to 6 people. So privacy is obviously a really important aspect of the system. These autonomous vehicles operate on demand on a dedicated infrastructure on a so-called guideway network. So you have no mixed traffic there. This is super helpful to actually allow the vehicles already operating right now autonomously on this system. And you have no transfers. The whole network is completely connected, so you can reach every station from every station. The on-demand aspect supports the convenience and flexibility for the customers, and is centrally operated, so you can ensure that there is no congestion on the links in the systems by either optimizing routing, for example, or just leaving some passenger wait for a little bit in the station before you let them go onto the network. Capacity, as I just mentioned, is an important aspect to solve our mobility challenges. And actually, PRT is quite promising regarding the aspect of capacity when we compare to other public transport modes. Of course, a subway is offering a huge capacity due to the big train it is consisting of. However, PRT has the potential to reach a capacity compared to a light rail system or a bus system. We already do have some existing systems, for example, in London at the airport in Heathrow. Right now, the capacity is not that high due to head weights just at about 4 to 6 seconds. However, if we are able to decrease these head weights to about 0.5 seconds, we have the chance to be compatible with the other public transport systems. Since there are only existing small size installations of a PRT system, our goal is to use SUMO to analyze actually large scale PRT systems. If there's too much background noise, we are very sorry right now. Felix and we are in Bologna supervising a students project called Global Drive, and we are attending this conference from our Airbnb, and unfortunately it's under construction, this place. So we are very sorry if the background noises are too bad.
All right. So for today's talk, we've brought 2 topics. So on the one hand, as Franziska said, we want to outline our general approach to use regarding PRT and other modes of transport using SUMO. And we also brought some case study we recently did with some partners. Amongst those was the DLR. So in this case study, we took expertise and data of local administrations of a medium-sized city in the middle of Germany called Bad Hersfeld, as well as process data, mainly demand data from our project partner 7 Principles. I think you will also have the chance to hear from them during this conference. Our goal for the simulation, the specific case study, was to prove viability while not getting lost in details. So we didn't want to have micro simulations of every detail, but more get a general picture. The specific goals were designing the optimal transit network and to evaluate the different PRT system configurations. Since we're coming from academia, we are also, of course, focused on related literature, and instead of bringing a huge table, we brought some interesting collection because PRT literature is actually a great example for Gartner's hype cycle that you probably well know. The literature dates back to the early 70s, so 50 years ago. There was a big hype back then, reached a plateau at some point. There were great publications by Jörg Schweitzer, for example, and still today, there's great publications, for example, somehow related regarding DRT, demand responsive transit. But you might ask yourself, what is everybody doing? And I guess we all know main interest right now is probably autonomous driving. However, we don't see this as a bad thing because AVs will never unfold their full potential without central organization. And you might also think about dedicated guideways. So then you're getting closer to PRT already. That's why we think PRT research is still relevant today. We tackle this agent-based traffic simulation with SUMO in a general way, which consists of input being network and demand. We simulate infrastructure, vehicles, and their operation. We produce vehicle and infrastructure data as outputs, and we evaluate this data using a set of KPIs. We will get into how all of that works a little bit deeper now. So the inputs, of course, consist of an area that we select. That was, for example, the city of Bad Hersfeld. We collect and prepare data. For example, the demand data we obtained from 7 principles. We use SUMO's OSM export functionality, locate stations, model traffic and demand, for example, using Saga, and finally come up with a network design.
The goal when we designed this network was to minimize the travel time and the construction cost at the same time. As input, we assume we already have the potential given construction space, in our case, the roads of Bad Hersfeld. We knew already the location of the stations and the respective demand. So, of course, our objective functions were the travel time and the construction costs that we had to minimize. And to actually really get in the end a PRT system, a PRT network, we had to fulfill certain constraints. One of the most important constraints is actually that the graph has to be fully connected so that you can reach every station from every station. Additionally, you have to consider the capacity of each lane to ensure that you do not end up with a congested system in the end. And regarding the mathematical formulation, when you assign the flow on this network, you have to ensure that it's a feasible flow so that only stations are sources or sinks, and that you do not lose any flow at intermediate nodes or at some. This can be modeled as a multi-commodity flow problem, which was already done by a few authors, for example, Zheng in 2015. And with that, I would like to give you a short outlook. One of the questions we would like to address is how are actually the network design and the operating strategies affecting each other? Because if you break it down, make it super simple, you just would like to have a system with no congestion. You can either start by with a capacitated network design and do a static flow assignment. So you actually completely forget about the time. That's how it's done most of the time. Just consider the demand and would you want to connect the demand in the best possible way? Or you assume that you already know the network, you have a given network, and then you optimize your operating strategies, how you send the vehicles to the customers. In this case, of course, time is already taken into account. Our goal is now to combine these two aspects regarding operating strategies, especially the rebalancing, so the anti-vehicle flow. We want to take that already into account for the network design. And regarding the network design, we will go away from the static flow to a flow over time assignment so that we have the time in the network design process taken into account. You can see by that then at every single time step how the flow is spreading over the network. The reason why we are doing that is because PRT is a super flexible system and it's important to already include this flexibility in the network design process.
Okay, now that we theoretically achieved an optimal network, we can continue hands-on by building up the simulation. This, of course, consists of the vehicles, and that's quite straightforward since SUMO offers a lot that you can just use. You can model AVs using the Kraus car following model, parameterize it accordingly, and it will work perfectly. The taxi device enables DRT functionalities, so also no rocket science. And you can simply use the battery device and you will have a great way to simulate electric vehicles. Regarding stations, there's also been some work from Jörg Schweitzer. We basically took his design and implemented it using all the functionalities SUMO offers. So we just took bus stops for arrivals and departures. Parking areas can simulate the berths vehicles park in. Access lanes allow you to easily connect the OSM exported networks with the ones you come up with. We're also looking at merging because, as Franziska said, high capacity is one of the main advantages. So the SUMO zipper works great, and I don't think it has any drawbacks. But the good thing about implementing something yourself is that you actually know what's going on. So when we're producing a constant flow at the capacity limit, we sometimes ran into small problems that are actually, I think, a good thing, because that's exactly what you would want if you're simulating realistic traffic. You see now the cars slow down because they're afraid of crashing, and that's actually a good thing. But in PRT, we don't want it. We want them to run perfectly at the capacity limit. So we allocate time slots. We calculate when the vehicles are meant to arrive. We take their entrance speed, their maximum acceleration, deceleration, and basically compute their required static speed as well as the required acceleration or deceleration. So then we just deactivate the car following model and set the speeds manually. That looks somewhat like this. You see the blue cars are slowing down, green cars can keep their speeds, and at the exit, at the merging point, they will have an exact distance of 0.5 seconds headway. Of course, this is now a bit slower. It also works at the capacity limit, and yeah, it's just a fun little play thing. To be honest, we didn't need it so far in reality because we almost never operated the capacity limits. Another important thing is the operating strategies, which vary greatly in complexity. So we have dispatching as well as rebalancing. SUMO also has some functionalities, for example, nearest idle taxi or nearest open request. You can also combine these two heuristics and make it a little bit better, or solve a global assignment problem, which is of course more complex and will take a lot of calculation time. Same for rebalancing. You can idle randomly or just park in a depot, or you can try to predict passenger demand and come up with smart solutions. However, other artists, as well as ourselves, figured out that this doesn't yield great improvements compared to some good heuristics. So key takeaway here is just use what SUMO has and don't spend too much time on making it better on your own. You will just slow down your computation.
Now we go to some results regarding the case study we did in Bad Hersfeld. As already pointed out, the network is an important input. So we started with the mathematical formulation, started to connect the three stations, the parking slot in the north, the hospital, a park, and the train station. Of course, we couldn't take into account a lot of specific information about the city at this point. So we worked together with the city of Bad Hersfeld to improve that network, to make it fit exactly for this city. So one aspect was that they want to have just single lanes to have enough space for the POT system and still some space left for the cars they would like to send on the same road. And we implemented this network then in SUMO, as you can see in the picture in red, the network of the SUMO, of the POT system.
Okay, so to put things in a nutshell and to visualize our general approach, we took the specified inputs like the network infrastructure, the fleet configuration, the operating strategies, dispatching, rebalancing, as well as various infrastructure configurations. For example, we changed the number of berths. We run our simulations, let the vehicles drive around many times, finally get the output being trip info files, and then we just analyze them using a set of KPIs. Those can be grouped in 3 categories. For example, the level of service being relevant to the customer, like waiting or travel time. Financial viability, obviously important for operator or the city that thinks about a system, and sustainability, environmentally as well as socially. And yeah, comparing these indicators, we've brought some small example. You can, for example, check out fleet occupancy and waiting time and their relationship. The colors of the dots are different berth sizes, so the number of parking slots per station, and the size of the dots is actually the fleet size. So the key message here is that you can draw, for example, a vertical line and achieve a certain waiting time with completely different setups. You can have either a bigger fleet, you can build more parking spaces, and there's a great variety. So the takeaway here is there's no one size fits all solution. Our goal is not to develop this one algorithm that comes up with one specific perfect solution, or at least claimed perfect solution, but we want to show how everything interconnects and how there's different ways to go on from there. So you will also find our code on a GitHub repository hosted by DLR within the scenarios. We're happy to have you download it, and we'd also be happy to answer your questions via email. Just get in touch, set up a Zoom meeting, and of course also in the next minutes. Thank you for your attention.